Hey, grade 12s. Just thought I would start this lesson here with a little reminder of what I look like and a little update on what's going on here. So as you can see, I am back in my classroom. And as you can also see, I haven't got a haircut in like half a year. So that's why I'm wearing a hat. I hope you're all doing well. I just wanted to let you know that we've got basically 2 lessons left in fields before we're done. So that means we're really close. So if you're a little bit farther behind, now would be the time to just, take this week if you can, try to get yourself caught up. You got next week as well, and a little bit of time after that, but we're getting right down to the end of it. So if you got any concerns about what's going on, just let me know and we can work through it together. So there's going to be meetings happening next week if you want to come in and say hi, catch up, clarify something that's going on. I'll be contacting people if you're interested. So yeah, let's just keep at it. We're almost finished. I'm obviously missing all you guys and missing having regular classes, but the end is in sight, so let's keep it up, okay? Let's get to it. So we're just finishing with magnetic fields here, and I'm going to share my screen. If I can figure it out. I always struggle with this. Okay, here we go. And yeah, I hope you're all doing well. I'm sure that there's lots of you that are keeping busy one way or another, and I'm looking forward to being able to hear about what you guys got going on. So definitely reach out because I'm missing hearing from all of you. So it feels weird being back in the classroom and it's empty again. Let's do a small just overview of what I had assigned for you to do the past couple days, which was just to go over that magnetic fields review on your own. So all I'm going to do here is I think that we're all familiar with magnetic fields after reading through this, okay? The idea that we've got a north pole and a south pole and that our magnetic field goes from north to south should be something that I think that we should be pretty familiar with. Now, one thing that I know a lot of students struggle to remember is the right-hand rule. The right-hand rule is something that's just kind of a device for us to be able to remember which way that currents, magnetic fields, magnetic forces, and even velocities now we're going to get to are pointing in certain situations. So let's just go over the first 3, and then I'm going to introduce you to a 4th today. So right-hand rule number 1, we learned this in grade 11. Your thumb points in the direction of the current, and then the magnetic field is the direction that your fingers will curl in around the current carrying wire, and it'll make a magnetic field around it. Okay, so thumb current, fingers magnetic field. Number 2, this is a current carrying loop of wire. So not just a current carrying wire, not a straight one, a current carrying loop. Now it switches. Your fingers point in the direction of the current, and your thumb points in the direction of the magnetic field that's going to happen inside of that coil of wire. So kind of like opposites. And then number three was the force on a current carrying wire in a magnetic field. So if I put a wire that has a current in it into a magnetic field, it's going to feel a force. So now we've got 3 things going on. We've got force, we've got direction of current, and we have a magnetic field. So we need to use our hand like a 3-dimensional plane. Basically, our current is the way that our thumb points. So our thumb points in the direction of the current of the wire. The magnetic field is the direction that your fingers point. So our fingers maybe are going to point like this. And then what that would mean is the direction that my palm is facing is the direction of the force that that current carrying wire is going to feel. Imagine it's something kind of sticking out and pointing away from your palm like this. Okay, so current, field, force up like this. And then there's that one little exception is this is for a positive charge. If we were ever talking about a negative charge, it is just on the back side of your hand. That's it. So the force is just on the back side. Okay. There's plenty of videos out there as well that just kind of explain the right-hand rules as well. So if that wasn't, an explanation that helped you maybe enough, then I can link some videos for you as well that do a little bit more of a dedicated in-depth explanation of that. Just let me know, okay? But for our time being, we need to move on. We're going to talk about forces in magnetic fields. We're going to talk about a couple new formulas. Now, this formula first here is not new. F equals B times I times L. This is definitely one that we've seen before. So let's just do a small little recap of that one, and then we'll do a little example here. So remember, the force, the magnetic force, is equal to the magnetic field multiplied by the current multiplied by the length of the wire. So a current carrying wire produces a magnetic field. If this wire is in a magnetic field produced from some other source, there will be a force exerted on that wire by that magnetic field that it's sitting in. Through experiment, this was found to be the case, and that there's a force on the wire that can be calculated by this above formula. It's a really straightforward formula. To use the above formula, though, we have to always assume one thing. We have to assume that the magnetic field is perpendicular to the current. And if they're not, then we have to use components. Now, what that's technically saying is that this always has a little sine theta here. It really technically does. But what's sine theta of if theta is equal to 90? Right? Sine of 90 degrees, if I take my calculator here, we should remember this. And I know a bunch of you have your calculus exam coming up, so maybe you should, know that. Sine 90 is just 1. So if it's sine 90, it's just BIL, okay? So a 10 amp north current flows through a 2-meter long wire. The wire is in a magnetic field with a strength of 6 Teslas at 30 degrees west of north. What is the magnitude and direction of the force exerted on the wire? So what we have going on here is we have a current of 10.0 amps north. And then we have a length of wire, L is equal to 2.00 meters. And our magnetic field, which is B, is equal to 6.00 Teslas, and it's 30 degrees west of north. Okay. And then we are trying to find FB. Okay. So let's write out our little scenario here. Let's do our same little thing here. We always do this: north, east, south, and west. And let's write out this actual scenario. So we have got a current going north, and then we have a magnetic field going 30 degrees west of north. And you know what? I'm actually going to extend that all the way up to there. So that is the magnetic field. But the key was here is that we're only concerned with where the current and the magnetic field are perpendicular. So what we're concerned with here is the component of the magnetic field that is perpendicular to the current. That's the only one. That's the only amount of the magnetic field that's going to apply a force to this current carrying wire. We're only concerned about that. So what ends up happening then is we have B perpendicular, which is just the X component of our B, right? So it would be 6.00 sine of 30 degrees, right? It's like we're just breaking it up into components again. We're doing a SOHCAHTOA, right? So it's the opposite over the hypotenuse, we're doing the opposite from the angle, right? So that's how we're getting opposite over hypotenuse equals the sine of the angle. And this is our hypotenuse. So it's that simple. So basically what ends up happening here, and you could also think about it this way, is just FB is equal to BIL sine theta. and B is just 6, and sine theta is just sine 30. So we have our little, there we go, and we can just plug these all in. So B is 6, I is 10, and L is 2, and sine of 30 degrees. So FB, I'll write it down here, FB is equal to 60 newtons. Now, what is our direction? Now we have to use our right-hand rule, right? So our current is going north. Our magnetic field is going east, sorry, complete opposite, west. Where does that mean my palm is facing? Up, right? So our direction here is going to be up. There you have it. So we've got one more page here that we need to do, and then we literally will just have one last lesson after this to just finish up fields, and we won't get to electromagnetic induction or circuits, unfortunately. But if you are interested in that stuff, I will post all the resources on the classroom so you can look into it over the summer if you have a chance. All right, so charges and magnetic fields. Magnetic force. Current is defined as the flow of positive charges. The motion of charges produces a magnetic field. There does not have to be many charges moving in order to produce a magnetic field, though. Actually, a single charge can produce a magnetic field. So charges feel a magnetic force in a magnetic field if two things occur. Either A, it is moving, or B, the velocity of the charge is perpendicular to the magnetic field. Both of these have to be happening. Okay, if these two are happening, we'll move to the next page, and we have a new right-hand rule. We have a scenario here where we're going to have a velocity happening. So right-hand rule number 4. This is all about the force on a moving charge in a magnetic field. So we're not now worried about a current carrying wire moving. We're worried about an actual charge itself, a charge moving. This rule is just a variation of right-hand rule number 3. It's very similar. So we're going to just use the same, keeping our hand open. Now, in this case, our thumb points in the direction of the velocity of a positive charge rather than the current. The magnetic field is the direction that our fingers are pointing, and then our palm, again, like it was, is the direction that the force that the positive charge is going to feel. Okay, so imagine it pointing away from your palm. Here is a very important note. Note, if we are looking at a negative charge, the direction of the force is in the opposite direction of what the positive charge would feel. So if I had a positive charge and it was going off my palm going up, that would mean my negative charge was going down. If I had a scenario like this and my charge was feeling a force to the west, the negative charge would feel a force to the east. Okay? So let's do a couple small examples. I'll show you a new formula, and then we'll do one last example and we'll be finished. So example, a positive charge is moving east in a magnetic field that's pointing upwards. What is the direction of the force exerted on the charge? So a positive charge is moving east in a magnetic field pointing upwards. So moving east, that's my thumb, that's my velocity, the direction of the velocity. Magnetic field is pointing upwards, that's my fingers, so those are going to be pointing up at the camera like this. Where is my palm facing? South, right? My palm is facing south. So that's our answer. South. Now, an electron is moving north in a magnetic field that is pointing west, which is like that. Sorry, like that. So north and west. What is the direction of the force exerted on the, here is my hint for you.
This announcement is for heavy book teachers as well as aesthetics and hairstyling.
Okay, there's just an announcement going on. I'm just going to talk over it. So the electron means that it's a negative charge. So if my palm is facing upwards, remember the negative charge is the opposite. It goes off the back of the hand, which means that my direction of the force is actually going to be down. Okay. Normally at this point, I would do a small little derivation of where this formula comes from. If you're interested in the derivation of where the formula formula comes from. You can check my PDF filled in notes files, okay? For the time being, my video is quite long already here. I'm just gonna write down what the formula is. It is the magnetic force on a moving charge. So the magnetic force is equal to the magnitude of that charge in coulombs multiplied by the velocity of that charge multiplied by the magnetic field. And we're looking at the magnetic field again perpendicular to the motion, so we have to add that sine theta at the end. Okay, so just a reminder of all the things that we're measuring here: newtons for force, right? Coulombs for charge, meters per second for velocity, and Teslas for our magnetic field. So those are all of our things here. And then what is this sine theta? This is just the angle between, I'm going to do B/W, means between the velocity and the magnetic field. Okay, so where does that come from? You know what, it is really just a derivation of FB equals BIL. There's some little changes that happen with the B and the I, and well, the B stays around, but the I and the L. It would take me a little bit to explain. Like I said, just go check the notes if you're actually interested in that, but we don't need to know that for our scenario right now. So let's do an example and then we'll be done. A charge of positive 1 coulombs moves at 5 meters per second, 30 degrees northeast in a magnetic field of 6.0 Teslas. What is the magnitude and direction of the force exerted on the charge? So this is going to be kind of like almost like an inclined plane type problem, because what we have here is we have a velocity moving 30 degrees northeast like this, right? And then that would mean that let's write that down. Oh, I just wrote down the magnetic field. That's okay. Magnetic field is 6.0 Teslas east. So that's actually going straight east like this. And then we've got the velocity is equal to 5.0 meters per second, 30 degrees northeast. And like we were with the last one, we're only concerned, so this is velocity, this is magnetic field, we're only concerned with the perpendicular component of the magnetic field. So we're only concerned with B perpendicular. And now we've got a scenario where our B perpendicular isn't quite going straight north or south, but if I kind of rotate it like this, now I've got a scenario that's a lot easier to look at, right? I've got velocity with my thumb going this way, and I've got, oh man, this is gonna be hard to do with my hand. I've got my magnetic field going downwards. So maybe if I do it like this, there we go, right? So then my palm is facing down. So that means that my magnetic force, my magnetic force is going to be going down into the paper, okay? So that's what we're trying to find is magnetic force. We've also been given the charge. The charge is just 1 coulomb, positive. And that's all the information that we need. We're just trying to find force. So the only real super tricky part about this is, you know, keeping in mind our angle and everything, but also just knowing which direction that magnetic force is going to be going in. And we're just using that right-hand rule number 4 for that. So QVB sine theta. Q is 1, V is 5, B is 6, and sine of 30. I mean, realistically with these questions, whenever you see that angle, it's just sine of that angle. For any purpose that we're doing, I'm not going to really ask you to find like the complementary angle or, you know, the supplementary angle or anything like that. Usually just I give you an angle, that's the one that's going to be packed on the sine theta, okay? So FE times all that stuff, plug it into your calculators, and you get 15 newtons. And then just a reminder, right? That is our velocity down, really hard to south is the perpendicular. So my palm is pointing into the paper. So down is our direction. And that's a B, not a D. There we go. Down. So that's our final answer. And yeah, that's actually it for today. So I've got a visitor here that I need to chat with. So I'm going to leave you all with that. You can work on the associated practice problems with that. And you know what? Just a reminder again, just do the best that you can right now, okay? Because things are kind of crazy right now, and I'm feeling for all of you out there. So just keep it up. Know that I'm here if you ever need to chat or anything like that as well. Okay. Take care, and we'll talk to you soon.